All right, this is Charlie Thompson. Welcome to Lab 13 Maps. Here's a link to the Google Doc. This map assignment is going to be submitted via Canvas as a Google Doc, hopefully. And when you do that, make sure that you share the editing privileges with me. It's not enough just to let me see it. You need to allow me to comment on it, and that way I can give corrections and you can know what you've done wrong and how to avoid doing that in the future. So you're going to share this as a Google Doc. Make sure that you give permissions. I will update this. This is one Prelab video. I'm making another one, so when you see the assignment again, there's going to be two Prelab videos. Here is a link to the USGS topographic map sheet. It's a guide to the symbols so that you know what the symbols on the map actually represent. So the key concepts for this lab, when you're done with this lab, you should be able to define the concept of map scale and explain the difference between large and small scale maps. You should be able to use a ruler or scale bar to find distances on a map, find steep and shallow slopes, use contour lines and spot elevations to find elevations, use relief and horizontal distance to find the steepness of slopes expressed either as degrees or as a percent. And finally, evaluate the aspect of slopes. So section 1 is on scale. The first thing we talk about is scale. Scale is the ratio of distance on the map to the distance on the ground. So a 1-to-1 scale map, 1 unit on the map would equal 1 unit on the ground. It would be the same size as the ground. A 1-to-2 scale map would mean that it's half size. A 1-to-4 scale map would mean it's a quarter of the size of whatever it's representing. Very common scale for maps in the United States is 1 to 24,000, which would be 24,000 times the map is 24,000 times smaller than the area on the ground. And when you're talking about map scale, there's 3 ways of expressing scale. There is the representative fraction. 1 to 24,000 is a representative fraction. There aren't units because they're the same on both sides. So 1 inch to 24,000 inches, 1 centimeter to 24,000 centimeters, 1 meter to 24,000 meters. Doesn't matter what it is, the units on both sides are the same. And that's with a representative fraction. With a written scale, for example, 1 inch equals 4 miles, the units are different. So 1 inch equals 1 mile is a pretty common written scale. 1 inch equals 2,000 feet would be another example of a written scale. So with a written scale, the units are different. And finally, there's a graphic scale or bar scale. And usually bar scales will have larger units on the right and then smaller units on the left. So this is 0 to 4 miles, 4 to 8 miles. And then on the left-hand side, there's 4 miles divided up into 1-mile segments. So you can get a more precise measurement. That's why they include the more precise measurements on the left-hand side. Scales are small, medium, or large. So here is a graphic showing different map scales. So starting with the smallest, 1 to 3 million. So 1 inch on the map is 3 million inches on the ground. A large scale, 1 to 24,000. The smaller the denominator, the larger the scale. The larger the denominator, the smaller the scale. Small scale maps have small detail of a large area. This would be like a map of the entire United States. So you can see all of it, but you can't see a lot of detail. A large scale map, for example, 1 to 24,000, has much more detail, but it's a smaller area. So at a 1 to 24,000 scale map, you'd probably need 6 to 8 maps to cover all of Sacramento. Even in a city as small as Davis, you might need 2 or 3 of these maps in order to cover the whole area. So another way of thinking of this, to keep it straight in your head, the difference between large scale and small scale, it's a fraction. So 1/3 millionth of Bill Gates' money is clearly way, way less than 1/24,000th of Bill Gates' money. So we want to find the representative fraction for a world globe. And the world globe is 61 centimeters. Earth's diameter is 12,756 kilometers. We want to get this into a representative fraction in which the units are the same units on both sides. So we've got 61 centimeters, and the ratio is 61 centimeters to 12,000 kilometers. So the first thing we're going to do is multiply the denominator by 100,000 because there are 100,000 centimeters in 1 kilometer. You could do the math more slowly by saying, well, there's 1,000 meters in a kilometer, so let's multiply it by 1,000, and then there's 100 centimeters in a meter, so let's multiply it by 100 after we do that. Or you could just multiply it by 100,000 because there are 100,000 centimeters in 1 kilometer. So now we have 61 centimeters to 1,275,600 centimeters. So at least the units are in both sides of the equation are in the same unit. Now what we have to do is divide both sides by 61 in order to get the denominator or the numerator down to 1. So we need to divide the top and the bottom by 61, and we end up with 1 centimeter to 20,911,000 centimeters. Rounded, that would be a 1 to 21 million scale. So the scale of that map as a representative fraction would be 1 to 21 million. So there's a couple globe questions, a question about our classroom map. If you're planning a trip to San Francisco and you wanted to be able to unfold the map, so the trip on the ground is 160 kilometers, the map in your car is 1.5 meters wide. So you're going to have to upscale the kilometers to meters and then divide everything by 1.5. And then if you want to do the same thing with a more detailed map, that would be a larger scale map. What would that scale be? If you're planning to paint a local playground and make a map on the ground that's 10 meters along the equator, what scale would that be? So moving on from scale, we're going to measure distance. And here are 3 graphic scales or bar scales. This is the type of scale bar that you'll see on a U.S. Geologic Survey topographic map. It has kilometers, it has miles, and it has feet. Once again, the primary scale on this side, it's whole kilometers, 1 kilometer, 2 kilometers. So the whole scale is 3 kilometers wide. In this lab, we're just going to be using measurements that have already been done, but once you start doing it for yourself using a real map and a real scale, you have to remember that there's a whole nother unit here. So if you just looked at this, you'd say, well, this scale bar is 2 kilometers wide, but that's 1 kilometer, that's 2 kilometers. There's a third. It's really 3 kilometers long. A lot of students make mistakes and don't include the length of the extension scale when they're measuring. So the 2 main techniques for measuring distance on map, the first one is you can lay down a piece of scratch paper. If you wanted to measure from point A to point B, you'd make tick marks on your scratch paper, and then you're going to plop the scratch paper down on the scale bar. So they've centered the one tick mark, the right tick mark, at the 3 kilometer. And you'd have to figure out where to put it, but you're going to put the right-hand side on one of the whole numbers so that the left-hand end is someplace in the more precise in the extension scale. So we've got 1, 2, 3 kilometers, and then looks like these are 100 meters, so 903.9 kilometers. Would be the approximate length of that. In fact, 3,950 meters, they're saying more precisely. On the test, I would just hope that you could get it to 3.9 kilometers using this type of scale. So the other way of finding map scale is to use a ruler and map scale. So the first thing you need to do is measure the distance in inches. Then you convert that fraction to a decimal. Multiply that decimal length that you got by the feet per inch on the map, and that'll give you feet on the ground. For example, 1 to 24,000 scale map has a scale of 1 inch to 24,000 inches. 24,000 inches equal 2,000 feet. So the scale of 1 to 24,000 is pretty convenient. 1 inch on the map is 2,000 feet on the ground. So if you measured 1 inch on the ground, that would be exactly 2,000 feet. If you measured 1/16 of an inch on a 1 to 24,000 scale map, you'd take that 1 over 16, you'd convert it to a decimal of 0.0625 inches. You just divide 1 by 16 in your calculator. Then you multiply the decimal that you got by the number of feet on the ground, 2,000, to get 125 feet. So 1/16 inch on your ruler, or rather 1/16 inch on a 1 to 24,000 scale map, would equal 125 feet on the ground. So the topographic map number 2 deliberately doesn't have the map scale on it, but we can figure it out. So on topographic map number 2, And here is topographic map number 2. On topographic map number 2, these orange lines are section lines and they are exactly 1 mile apart. So if you measured those lines, you'd know how many inches on your map equal 1 mile on the ground. So one of those squares is 2.64 inches on the map. So now we know that 2.64 inches on the map equals 5,280 feet on the ground. There are 12 inches in a foot, so if you multiply the number of feet in a mile by 12, you know that there's 63,360 inches in 1 mile. So now we know that 2.64 inches on the map equals 63,360 inches on the ground. So what we needed to do was get it instead, we wanted to get the scale. So when you're figuring out the scale, the units on both sides have to be the same. When we started, we had an inch on the map to 1 mile on the ground. But what we really want is inches on the map to inches on the ground. So once we have 2.64 inches on the map equals 63,360 inches on the ground, if we divide both sides by 2.64, you get 1 to 24,000. And so the map scale then is 1 to 24,000. And then there's several scale questions. USGS used to make maps at a scale of 1 to 63,360. Maptools.com sells a set of special rulers. Those rulers are amazing. Instead of being a normal ruler, the divisions, the lengths on the ruler are what the length on the ground is, because they've already figured out the scale. So for example, the 1 to 24,000 scale ruler measures in increments of hundredths of a mile. So 1 increment on the ruler would equal 1/100th of a mile on the ground. Some fraction questions for you to deal with. If you measure 8 7/16 inches on a 1 to 100,000 scale map, what is that distance on the ground? Section 3 is about contour lines. Hopefully you watched the other video that has a brief overview of contour lines, but some of the basics about contour lines. Each contour line connects points of equal elevation. So if you walked along any one contour line, you would always be at the same elevation. The contour interval is the vertical difference in elevation between two adjacent contour lines. So for example, if the contour interval was 10 feet, that means that each line is going to be either 10 feet higher or lower than the line next to it. Contour lines are printed in brown on topographic maps. Every fifth line is an index contour with a thicker line width and its elevation labeled. So for example, on topographic map number 2, you can see the index contour lines, for example, 6,800 feet, 7,000 feet, 7,200 feet. So those are all index contours. Contour lines separate areas of higher elevation from areas of lower elevation. The varying degrees of steepness are obvious. Where the lines are very close together, for example, right here, it's very steep. Where the lines are far apart, for example, right here, that means it's flat. So the closer the lines are together, the steeper it is. And in fact, if you notice, for example, down here, panoramic cliff, the lines are really, really close together because it's a cliff. Contour lines crossing stream valleys form a V pointing upstream. So on this map, right in here. So you can see the elevation down here is 4,200 feet from the index contour, and the elevation up here is 5,200 feet. And where the stream is going upstream, and we know it's going upstream because we can read the numbers off of the index contours, you can see that the lines make a V pointing upstream. So alligators swimming upstream is one way to remember that. Hilltops are indicated by a series of closed concentric circles. So for example, Mount Broderick, Liberty Cap, Panorama Point, the top of Half Dome. You can see that the circles get smaller and smaller and smaller, indicating that you're approaching a hilltop. Given a large enough map, contour lines always form a closed circle, although on a smaller map, they often run off the edge. They only touch the contour lines where there's a steep cliff, and they never cross. Contour lines, just like all the iso lines, the isotherms, the isobars, they don't cross. Concentric closed contours indicate a hill, and there's a similar pattern with hachur marks, small tick marks on the downslope side indicating a depression. Otherwise, you wouldn't know if you're going up or down. None of these maps have hachur marks, so you don't need to worry about that for now. When a map is showing a depression, the first hachured contour line is the same elevation, oh yeah, thanks for the typo, same elevation as the adjacent lower contour line. To determine the elevation of a hilltop, add 1/2 the contour interval to the elevation of the last contour line. So, if we're going to look at this map again, let's get rid of you, make you bigger. So, for example, right here, and in fact, we can figure out what the contour index is. So we know that each of the indexes is 200 feet apart. There's 5 lines in between, so this has to be a 40-foot contour interval. So if you take what the difference between 2 index contours, divide that by 5, that'll give you the contour interval for each line. So each of these lines is 40 feet higher than the line before it. So this is 6,800, 6,840, 6,880, 6,920, and then because this is the summit right here, 6,920 plus half of 40 is 20 would be 6,940. So the elevation of this hilltop would be 69,040 feet above sea level. I go through how to calculate the contour interval, talk about spot elevations. So the 2 ways of finding elevation on a map are either you can use the contour lines, or sometimes maps have spot elevations, and a couple different ways. So BM34, that's a benchmark. Somebody's actually surveyed that site right there, that X, it's 34 feet above sea level. Often mountain summits, like Point Reyes Hill, 1336, Mount Vision, 1282, those are the spot elevations of the summit of those hills. Sometimes they have triangles, like this 355, that's 355 feet above sea level. The little triangle indicates that there's a marker there. So if you were to walk out, you'd find a little disc with information on it. Usually says property of USGS, fined for removal. Yes, down here, BM 552 with a little triangle, 173 with a triangle, there would be markers there. BM 217, BM 13, there'd be no marker. Like right here, BM 323, right at the intersection, the elevation is 323 feet above sea level. So there's spot elevations, there are contour intervals. You can use both of those to find elevation above sea level. USGS maps have colors that they use for different features. Black is for human or cultural features like roads or buildings. Blue is for water. Brown is for contour lines. Green indicates woodland color. They have different patterns in the USGS symbols PDF that I've attached, or rather there's a link to in the assignment. You can tell the difference between scrub and vineyards and orchards or forest based on the pattern that they use on the map. Red ink emphasizes important roads like freeways used to show public land subdivision lines. Purple ink, and none of the maps that we're using have purple ink, but purple ink is used to show revisions. So if it's an updated map, often the updates still use purple ink so that you can tell that those are revised. It's something new. To determine elevation, anything touching a contour line is the elevation of that contour. Halfway between 2 contour lines, the elevation is halfway between. Sometimes lakes have the elevation of the lake surface printed in blue on the lake. If the contour touches a lake shore, the elevation of the lake is the elevation of the contour. And then some elevations are spot elevations with an X or a triangle sometimes, but not always. So example 1, we want you to look, there's another typo. Thank you. Above the word raise, there's a benchmark. So find the elevations of some of these benchmarks. Oh, actually, that was an example. Example, there are 5 spot elevations on Topo Map 1. Above raise, there's a benchmark with an elevation of 283. Just below the word raise, there's a benchmark with an elevation of 552. And under the S in raise, there's another benchmark with an elevation of 217. 5 spot elevations in the lower left. Ah, yes. So 552, 283, 217, all of those. Those are all spot elevations. Benchmark 13, 173. Those are all 1, 2, 3, 4, 5. Those are the 5 spot elevations. So you're supposed to answer some questions about elevations on the map. Chock full of typos. What is the benchmark by the blacksmith shop? What's the highest elevation for the spot elevation shown by a triangle symbol? So you'd have to look at the whole map to find that. What's the elevation of the quarry found between the Call building by Abbott's Lagoon and H Ranch? List all the contour line elevations you'd cross if you walked from the benchmark at the blacksmith shop to Schooner Landing. So there's a trail, and I want to know if you're walking along that trail, what are the contours that you would be crossing over? So for that, you'll have to probably zoom into the map, if I knew which way zoom was, and then look at the contour elevations. So right here we have an 80 foot. So the first one would be 80, and then 160, and then 240 would be the elevations as you walk from Drake's Head up to this spot elevation of 222. Those are some of the contours that you'd be crossing. What is the contour interval for the map? What are the types of roads? You're going to need to look at the symbols for that. What's the elevation of the summit of Mount Broderick? The vertical distance between two places is relief. So using topographic number 2, what's the elevation of the summit of Glacier Point? What's the elevation of the stream gauge? And then what's the relief between those two locations? Use topographic map number 2 to answer which of the following points is on the steepest slope, which of those points is on the flattest slope. And for that, you don't need to do any math. You're just looking and seeing where the lines are, how close together the contour lines are. Whichever has the contour lines that are the closest, that would be the steepest slope. Whichever one of those letters is on the lines that are farthest apart would be the flattest slope. Speaking of slope, the formula for slope is rise over run. Rise is the vertical distance or relief, and run is the horizontal distance. So in this example, we have a rise or the relief of 20 meters and the horizontal distance of 100 meters. There are 2 common ways in this lab that you will be asked to express slope. The first is slope as a percent. So 100% slope means that for every unit you go over, you go up 1. So that would be a 45-degree angle, would be 100% slope. For every unit you go over, you'd go up 1. The rise would be 1, the run would be 1. That would be 100%. So to find the slope as a percent, you just divide the relief by the horizontal distance. In this case, the relief is 20 meters. The horizontal distance is 100 meters. So the slope would be 0.2, which is the decimal equivalent of 20%. So to find the slope, you divide the relief by the horizontal distance, and then multiply that by 100 to get the percent slope. The other way that you're going to be asked to express slope would be as feet per mile. So I'm not asking you how many feet are in a mile, but if you extended that slope for a mile, what would be the vertical relief given a run of 1 mile? So the easiest way to do that is you divide relief by horizontal distance, and in your calculator, when you do that, in this example, you'd have 20 divided by 100 is 0.2. So then you'd take the 0.2 and you multiply it by the number of feet in a mile. So remember, 100% slope means for every unit you go over 1 mile, you would go up that much 1 mile. So if the percent slope was 100%, you'd multiply 5,280 by 1 to get 5,280. If it was a 50% slope, you'd go over 5,280 and you'd go up half a mile. So in this example, we've divided the relief 20 by the horizontal distance of 100 to get 0.2. And then we're going to multiply that by 5,280 to get the answer expressed in feet per mile. So 0.2, 5280 So 1056 would be the slope expressed in feet per mile. There would be 1056 feet per mile. There's some examples. In fact, this example, it's the same example. I didn't remember that was there. So 0.2 times 5280 is 1056. So the slope in feet per mile is 1056 feet per mile. Another example, on topographic map number 1, it's 1.65 inches from McClure's Ranch to the H Ranch. The buildings at McClure's Ranch are at 80 feet, and the buildings at H Ranch are 160 feet. So we know the relief is 80 feet. If there's 1.65 inches and the scale of the map is 1 to 62.5, we multiply 1.65 by 62.5 equals 1,125 inches. 1.65 inches on the map equals 125 inches on the ground. But we want feet. So the distance between those ranches is 8,593.75 feet. So we have a rise of 80, a run of 85.93, which works out to 0.009. If we multiply that by 5280, we know that the slope is going to be 49 feet per mile. And 0.009 multiplied by 100 is 0.9. So the slope as a percent is 0.9% in feet per mile. It's 49 feet per mile. So, yeah, I feel like I should go over that again. If there's 1.65 inches between places, we know how many inches there are on the map. And then we need to figure out how many inches that is on the ground. We know that 1 inch on the map, because the scale of the map is 1 to 62.5, 1 inch of the map is 62,500 inches on the ground. We multiply that by 1.65, because that's how many inches we had on the map, to find inches on the ground. We take the inches on the ground, we divide that by feet, so that we know that 1.65 inches on the map equal 8,593.75 feet on the ground. We know that the slope, we have a rise of 80, a run of 85.93, so the slope is 0.009. Multiply that by 5280, we get 49 feet per mile. Multiply 0.009 by 100 to convert it to a percent, we get 0.9. Make sure, because I think the easiest way to do this is you divide the rise by the run, multiply that number in your calculator by 5280. I would probably then divide by 5280 to get back to 0.009 and multiply that by 100. Make sure that you multiply by 100 to give me the final percent. If you say that it's 0.009%, I'll look at it and say, oh, that's sad, you're off by 100-fold. That's 100 times wrong. So you've got to make sure to convert it, multiply it by 100 when you're all done to convert that decimal percent into a percent. And then there's a bunch of questions. Use topographic map number 1 to find the slope. What's the elevation? What's the horizontal distance? What's the slope as a percent? Slope in feet per mile. Some more examples from topographic map number 2. The recommended slope for a zip line is 6%. I have no idea what the slope is of any of these, of the 3 slopes, from Sentinel to Glacier Point, from Glacier Point to Happy Isles, from Liberty Cap to Panorama Point. I have no idea what the slope of those is, but I just saw a YouTube video of a summer camp that decided, it'd be fun to make a zip line. And because they didn't know what they were doing, they made it way too steep. And so they ran a test run with a flour bag and it just exploded because it hit a tree at the end because it was way too steep. So, in honor of the zip line of death, I want you to tell me which of the slopes would be best for a zip line. Doesn't mean it has to be good, just which would be best. Which would be worst? I want to know what the steepest of those slopes is. The last thing we're going to talk about in this lab is aspect. An aspect refers to the compass direction that a slope faces. In the northern hemisphere and the southern hemisphere, these are different. In the northern hemisphere, south-facing slopes are exposed to more direct sunlight. North-facing slopes are going to be shadier, they're going to be cooler because they get less energy from the sun. They're cooler because they're cooler, there's more water because there's more water, there's more vegetation. This is also where you'd expect snow to accumulate to start a glacier. as opposed to the south-facing slope. You'd expect to find less snow, fewer glaciers, fewer vegetation on the south-facing slope. And then aspect is you could give it as north, south, west, or east, or the intermediate directions, northeast, southeast, southwest, northwest. So here is a map that I made of Mount Fuji, color-coded by aspect, where the north-facing slopes are black, the east-facing slopes are green, south-facing are yellow, and the west-facing are orange. And here is Mount Fuji as it looks in Google Maps. And in Google Maps, it's really interesting. The direction of the sunlight, hopefully you can figure out which side is sunny, which side is shady. It's not accurate. It doesn't look the way it really looks in reality. But if they don't get the light coming from the direction that they used, and I'm not going to tell you what that direction is, that's part of your assignment, but the direction that the light is coming from, if you actually have the light look natural, your mind plays tricks on you and it looks like a hole rather than the mountain. So they actually have to, for whatever reason, the way our brains interpret shade, and if you want a mountain to look like a mountain, you got to have the sun angle coming from this direction. If you had it coming from a realistic direction, we live in the northern hemisphere, so we always have to look south to see the sun, but then this would look like a depression, a hole. It's really weird. So the last is to answer some questions about aspect and then use one of the topographic maps to determine which direction some of those slopes are facing. And really quickly, I just want to give you a look at some of the pictures I've taken over the years that illustrate aspect, I think, really well. This is flying over Southern California. You can see these are south-facing slopes. You can see they're bare. There's very little vegetation as opposed to these north-facing slopes. There's a little north-facing bit, little north-facing bit, little north-facing bit. The north-facing slopes have much more vegetation, again, because they're shady. This is flying over Mono Lake. These are lateral and terminal glacial moraines. Here's more lateral. There's a lateral moraine from glaciers that flow down out of the Sierras. But I was really interested in the snow down in this corner. So here, south-facing. In fact, you can see the north-facing slopes are in shade, and the south-facing slopes, the ones that are most directly south-facing, the snow has all been melted away by sunlight. Another view from the same trip showing the south-facing and north-facing slopes, south-facing and north-facing slopes. The north-facing, north-facing, north-facing slopes have much more snow. And finally, just another cheesy example of south-facing and north-facing slopes. So that's it for Lab 13 on maps. I hope you enjoy maps. I hope it's a fun lab for you, and good luck.